Here are solutions to homework set number 8 for ECE 461 control systems. Now, this problem looks at given a fourth order system. This is a model of a 10th order RC filter, one of the earlier problems we had this semester. Just take the four dominant poles. Let's design a feedback control system to control the tip temperature. So the first problem is design a gain compensator, K of S is just a gain K, such that I get the fastest system possible with no overshoot. Translating what that means is when you draw the root locus, I've got four poles. These come together, split apart. I'm designing for the breakaway point. That's where this pole's gone as far as left as possible. Biggest gain I can get without any overshoot, without any complex part. So the first step is you've got to find the breakaway point. One way to do that is in MATLAB, input the system G of S, draw the root locus. Looks like this. And there's my design point. I want to place the closed loop pole at the breakaway point. Once I know S, at any point on the root locus, G times K is minus 1. So evaluate G of S at my design point. The minus sign is good. I'm on the root locus. Gain's wrong. Pick K to make the gain 1. In MATLAB, what I would do is input S. S is minus 4.5490. Find G of S at that point. Pick K to make the gain 1. So there's K. What that should do is my closed loop dominant pole is at the breakaway point, minus 4.54, and its conjugate. The 2% settling time should be 4 over that. Kp is the DC gain. That's just G of S as S goes to 0 times K. And K, the error for steady state input is 1 over Kp plus 1. If I then plot that in MATLAB, here's my closed loop system. That's the GK over 1 plus GK. There's my dominant pole. And I got two poles right there. So I'm at the breakaway point. Plot the step response, and here's what you get. Again, no overshoot like I expect. The poles are real. Here's the steady state error. I want to go to 1. So that right there is the steady state error. Again, pretty much what I expected. And the settling time is right around here, about 1.4 seconds. Problem 2. Suppose I'm allowed to have 20% overshoot. Now design a gain compensator. In that case, same procedure as before. Sketch the root locus. On top of it, add your damping line. 20% overshoot has a 2-to-1 ratio, so I go over 1 up 2. So on top of it, I'm going to freeze the root locus plot and plot the red dotted line. I'm going to go from the origin 0, 0 to minus 5 plus 10. With the red dotted line, or dashed line, that's my design point. Zoom in on that, I can find S. S is roughly minus 3.26 plus J is 6.33. Now, at that point, any point on the root locus, G times K is minus 1. Find G of S at that point. Pick K to make the gain 1. So K is 5.67. Finding the closed loop system, GK over 1 plus GK, I have a pole. There should be a pole where you placed it. Again, that's the whole reason I pick K. I pick K to put the pole at minus 3.18 plus J 6.30. There should be a pole where I placed it. There is, so everything looks good. The resulting response, 4 over the real part, your settling time, 1.25 seconds. Kp is the DC gain. G of S as S goes to 0 times K. K is just a constant. Error per step input is now only 0.18. Plot the step response, so this is no overshoot. This is with 20% overshoot. You can kind of see as I move along the root locus, I get a lot of advantages. I get a faster system, better tracking, but the trade-off is I now have overshoot. If you can tolerate 20% overshoot, I can get a much better system. That's gain compensation. Lead compensator. Suppose I could add dynamics to the compensator, add a 0, add a pole. If I do that, I can speed up the system. So I've got 4 poles. The pole that I want to get rid of is not the slowest pole, it's the second slowest pole. Keep the pole at S equals, close to S equals 0. That keeps the steady state error down. Get rid of this guy. That's causing problems with the root locus plot. Get it out of there. Move it out to minus 90. If I do that, then g times k looks just like g of s, but the pole at -9 is now shifted to -90. Now draw the root locus plot for the lead compensated system. Add the damping line. Again, going over 10, up 20. I'm looking for this point. And the reason for the times 10 is the root locus didn't get to this point. Make k big enough, eventually passes the damping line. That's the point that I care about. Read that off the graph, and it's -6.82 plus j 13.64. Basically zoom in on it. That's g times k. Pick k to make the gain 1. K is 120. So here's k of s. That's my lead compensator. To plot the step response, I'll then plot the closed loop, calculate the closed loop system, gk over 1 plus gk. The eigenvalue, there is one right here, and there really should be a pole at -6.8 plus j 13.6 because I picked k to put the pole there. So there should be a pole where I put it. And it's not exactly the same, but pretty close. Actually, it is the same. Okay. From that, I can tell you the response. The settling time is 4 over the real part, 0.58 seconds. Kp is the DC gain of g of s times the DC gain of k of s, 9.36. Steady state error is 0.09. If I plot the step responses, here is the first problem. Here's the second problem, gain compensated. Third problem, lead compensated. And notice the lead compensator gives you a faster system, better tracking. Kind of the best of both worlds. The problem with the lead compensator is as s goes to 0, or to infinity, that's my initial input. This has an initial input of 120 versus the gain compensated system. The initial input at t equals 0 is 5.6. So I'm really slamming the input. If I do that, I can make the system faster, but that kind of assumes that my input can actually shoot up to 120. Last part is come up with a circuit to implement k of s. So here I've got 3 degrees of freedom, or 4 degrees of freedom, 3 constraints. Arbitrarily, let's let this be 1 meg. As s goes to infinity, this is a short. S goes to infinity, the gain is 120, so this is 1 meg over 120. At high frequencies, the gain, at DC, s goes away, the gain is 12. So the total resistance is 82K. 8.29 is here, there's the remainder. Or another way to do that, that's a 10-to-1 ratio, so this is 9-to-1. Then finally the 0 shows up right here. The 1 over RC time constant is the 0, so 1 over RC is 9. R is 74K, solve for C, C is 1.48 microfarads. So this is one solution for that k of s. There are others. Problem 4. Now we're getting into PID compensation. The problem with the previous designs is I have steady state error for step input. If I add an integrator, I'll make it a type 1 system and there will be no error. So let's take the previous system, had 4 poles, add a pole at s equals 0. I now have no error for step input. Now designed for 20% overshoot. Now the problem with an I compensator is I just really slow down the system. This pole at 0.32 now goes to this pole at the origin, wherever it was, 0.32. These come together, split apart. Yeah, really close to the origin. Find that point on the root locus. Turns out it's -0.48 plus j 0.97. At that point, pick k to make the gain 1. So here's g times k at that point. Pick k to make the gain 1. So here's k of s. The closed loop system is gk over 1 plus gk. Again, here's your dominant pole. Find the eigenvalues, I can see them. It's -0.48 plus j 0.97, like I expected. The error for step input is 0, is type 1. Settling time is 4 over the real part. The settling time is now 8 seconds. So if I plot the step response, Here's the first problem, second problem gain compensated, lead compensated. Here's the PI compensator. Really, really slow, but the steady state error is 0. Circuit to implement it is I just have an RC. 1 over RC is 1.28. That's an integrator. Finally, a PI compensator. A PI compensator is P plus I over S, which I can rewrite as a gain K times S plus I over P, P over I over S. Factor out the, put this over a common denominator, pull out the P. So I've got a gain K, I've got a gain as 0, put the 0 anywhere you want. Well, I know what I want to get rid of. I've got this system, pull it 0, 1.21, 9, 23, 44. This guy's causing trouble. Get rid of it. What that does is that lets the root locus go further left, speeding up the system. So draw the root locus where I add a pole at the origin, get rid of the pole at minus 1.21, giving you G times K. Draw the root locus, find out where that root locus intersects your damping line. Okay, here's 20% overshoot, over 2, up 1. Say it is 0.4559, all that. Find that point S. It's minus 2.75 plus J 5.5. Pick K to make the gain 1 at that point. And here's K of S. That's my PI compensator. If I close the feedback loop, I have a pole at minus 2.75 plus J 5.5. I knew that because I picked K to put the pole there. No error for step input. It's type 1. Settling time is for the real part, 1.45 seconds. Plot, and here is your gain compensator. It's problem 1. Problem 2, gain compensator. This is your PI. And here's your lead. So the PI compensator is a little bit slower than the original system, but there's no error for step input. There's nothing stopping me from adding a second lead compensator and speeding it up some more, but for this homework set, that was good enough. Circuit to implement it is, here's my K of S. I've got 2 constraints, 3 degrees of freedom, so somebody's arbitrary. I like setting this 1 meg, this guy to 1 meg. As S goes to infinity, this is a short. S goes to infinity, the gain is 5.23, so this ratio is 5.23 to 1. So 1 meg divided by 5.23. Then the time constant, I had a 0 at 1.21. So here this 1 over RC is 1.21. What's happening is that DC, this is a resistor. High frequencies, this is a short, becomes, try that again. At DC, this is infinity, the capacitor dominates. At high frequencies, this is a short, the resistor dominates, and I switch at 1.2 radians per second. So that's what this does. That's where I switch. Knowing R, solve for C. C is 0.82 microfarads. So that is homework set number 8 for ECE 461.